Stellar mass black holes have been studied for approximately the last 50 years. Supermassive black holes have been observed for almost as long. However, the identification and study of intermediate mass black holes is still in its infancy. The reason for the lack of observations of intermediate mass black holes is not due to the lack of interest. On the contrary, intermediate mass black holes are thought to be the seeds of supermassive black holes, and so investigations into their nature could help unlock the mysteries of the formation of supermassive black holes. The study of intermediate mass black holes is such a new field because members of this class of black hole have been incredibly elusive. In the rare instances when intermediate mass black holes were identified, their classification was contentious, and later many were disproved. At present, there are only a handful of strong candidates for the intermediate mass black hole class. ESO 243-49 HLX1 is the first candidate intermediate mass black hole we will discuss. This source first hit the headlines in 2009 when its discovery was announced in the journal Nature. This black hole resides in a star cluster that is in orbit around the galaxy ESO 243-49, a galaxy that is 320 million light-years away from us. The designation HLX means hyperluminous X-ray source, while the one following is the same convention as other black holes we have discussed in the course. This is the brightest X-ray object in its host galaxy, outside the galaxy's core. Astronomers were quick to follow up on this source, making observations in multiple wavebands, from radio all the way through to X-rays and gamma rays. The temperature of an accretion disk around a black hole can give us an indication of the black hole's mass. The more massive the black hole, the cooler the disk appears to be. We have also found that more massive black holes tend to be brighter or more luminous than the lower mass cousins when they are actively feeding. ESO 243-49 HLX1 is approximately 1,000 times brighter than one of the stellar mass black hole at the same distance would be. The main difference observed between ESO 243-49 HLX1 and, say, our old friend Cygnus X1 is that it appears brighter and that its spectrum has been shifted towards the redder end of the spectrum. As astronomers watched over the next few years, we saw repeated brightenings of this source. ESO 243-49 HLX1 appeared to increase in brightness in a period of just over a year. The spectrum of this source was seen to change in shape with brightness. The time-dependent emission of ESO 243-49 HLX1 is very similar to the behavior of X-ray binaries, leading astronomers to believe that it is also a binary system. This means that the black hole ESO 243-49 HLX1 may be actively consuming a star. However, the cyclical nature of the outburst led some to suggest that this black hole may not be slowly sipping on the surface of a star, but may instead be ripping off larger chunks before gobbling them up in feeding frenzies. This would trigger outbursting behavior observed that mirrors that of outbursts of X-ray binaries. What could cause these periods of glut and fasting? The periodic feeding frenzies could be explained if the binary system's orbit is elliptical instead of circular. This means that the distance between the star and the black hole changes periodically during the orbit. When the star is at its furthest point from the black hole, no mass will be transferred from the star to the black hole. However, when the star is close to the black hole, the gravitational pull of the black hole will increase, allowing the black hole to attract large amounts of material from the star to the accretion disk. This famine and glut cycle has been suggested as a way to create the regular outbursts witnessed from ESO 243-49 Further studies have indicated that this black hole weighs in at about 10,000 times the mass of our Sun, and that resides in the centre of a dwarf galaxy that has been stripped and squashed during its interactions with ESO 243-49. These interactions may have triggered the formation of the star now feeding the black hole, and may have pushed it into an elliptical orbit that now feeds the beast. The cigar-shaped galaxy M82 is the home of another candidate intermediate mass black hole. M82 is a starburst galaxy where the stars form at a rate much higher than our own galaxy. The X-ray insert shows us a bright X-ray source named X1, which is possibly an intermediate mass black hole. M82X1 lies outside the galaxy's core. It was first detected in 1978 when it piqued the interest of astronomers due to its strange brightness. The reason that this source was thought to be so strangely bright is that it emits light at a much greater rate than we would expect to see if the source was a stellar mass black hole. The luminosity of M82X1 could have been explained by a supermassive black hole, and yet supermassive black holes are found in galaxy centres, while M82X1 does not lie in the centre of its host galaxy. This left astronomers with two options. The first option is that this black hole lies in the intermediate mass black hole range. If this was the case, it could explain the luminosity of M82X1. However, an alternative theory emerged. The idea that this may be a stellar mass black hole undergoing a feeding frenzy. If it is a stellar mass black hole, then it is accreting at previously unobserved gigantic rates. As more observations have been made of this source, the mass estimate of M82X1 has bounced between stellar mass and intermediate mass over the last 40 years. Today, evidence seems to be mounting in support of an intermediate mass black hole, with a mass estimated in the range of 400 to 100,000 solar masses. It's interesting to note, however, that M82X1's close neighbour, M82X2, has recently shown just how extreme accretors can get. In 2014, a team working with data from NuSTAR, Chandra and Swift satellites discovered that a previously observed X-ray source, M82X2, is in fact a class of neutron stars known as a pulsar. A pulsar is a rotating neutron star that shoots jets of emission from its poles. These jets sweep across our field of view as the star rotates, like a lighthouse beam sweeps over the rocks and out to sea. The striking thing about this neutron star is that it is 100 times brighter than theory predicts it could be. This means that M82X2 is one of the most extreme objects in our galaxy, and it could be used to help us understand how supermassive black holes could grow so quickly in the early universe. Enough about neutron stars though, let's get back to intermediate mass black holes. The next candidate intermediate mass black hole is XJ 1417 plus 52. This black hole has a mass that lies at the upper boundary for intermediate mass black holes, approaching the range of the supermassive black holes. Omega Centauri is a globular cluster found in the constellation of Centaurus. It is located almost 16,000 light-years away and is the largest globular cluster in the Milky Way. This star cluster may be home to our final example of a candidate intermediate mass black hole. Unlike the other candidate intermediate mass black holes, this black hole was not identified through its X-ray emission. Most likely, this black hole is not actively feeding, since there is no substantial food source nearby. The candidate intermediate mass black hole in Omega Centauri was inferred by observing the motions of stars using optical telescopes. The stars in the globular cluster move around randomly like a swarm of bees. The speeds of the stars are related to the total mass of the star cluster. From the observations of the star's motion, the mass, the center of the cluster, can be inferred. Different observations suggest that black hole with a mass in the range of 10 to 15,000 solar masses lies in the center of Omega Centauri. While there are a few other candidate intermediate mass black holes, their numbers are limited and many are still contentious. Many candidate intermediate mass black holes have been ruled out upon further study. The search for the elusive intermediate mass black hole is an active area of research, a field that is definitely ongoing.